All right, cool. Hello, everyone. Thank you all for coming to this meeting. I see we do have a bit of a dip in attendance. That's fine. I mean, not everyone can come to every single meeting. With that being said, I wanted to take the time today to end a lot of the sort of Fourier transform stuff that I was presenting last time. And I originally really wanted to have like a little circuit demo or some notebook like right off the bat. Unfortunately, that seems to have been side because the actual I want to show the derivation, like, okay, how do you go from that funky looking matrix all the way to a nice quantum circuit? And that might take some time. So your patience is much appreciated. But after this workshop, you should see something in the textbook as well as a little sort of software package that I will have you guys play around with, and I'll have some scenarios set up so you can actually see what the heck's going on when you feed something into that circuit. Now, with that being said, I'm going to go ahead and flip around, or I'll screen share, I should say. I say flip around as if there's like an actual chalkboard in front of me. But okay, here we go. Let's do share screen. Oh shoot, okay. Gotta set all this stuff up. All right. And let's see, where is the, okay, cool. Nice, okay, hopefully all you guys can see that. Oh, okay, looks like Amir here is here as well, awesome. Let me go ahead and open chat. Once again, if you guys have any questions, I will be able to answer them, via chat. So feel free to like stop me or go ahead and raise your hand if you'd like. So one of the things that I mentioned, like we did an example with a 1-qubit Fourier transform, and all that was it's 1 over the square root of 2, and it was this nice matrix here. And if I remember correctly, 1, 1, 1, and then -1. This is essentially a single qubit Hadamard transformation. And with the knowledge that we now have of what the general kind of formula is, to generate your Fourier transforms, you can extend this matrix to any number of qubits. So if I had 2 or 3 qubits, then this matrix would also kind of extend in size to account for the number of coefficients, I should say, or the number of basis vectors inside of your that generate your vector. Now, even though we have this matrix, there is one test that you should always do, and that's whether or not the matrix is unitary. And unitarity is something that is enforced by a large majority of, or I think it has to be there for quantum operations. I say majority because measurement, and there are like 1 or 2 exceptions to that rule. Measurement being, I think, the main one. But the idea behind unitarity basically is if we can represent all of our quantum operations with one matrix, essentially. So you got to remember that if I given some qubit here, and in this case it's just a singular qubit, so then we have some coefficient in front of our one of these basis vectors, and then another coefficient in front of your other basis vector. So you have 2 basis vectors that are orthogonal to each other, and some coefficients which tell you how much you need of each vector. So the idea behind for this representation of quantum computing, at least, is that I can take my vector and I perform some matrix multiplication, and then eventually I'll just get another vector out here, and everything will come up sunny side up. So you'll get all your information that way. Now, if this matrix, one of the requirements, sorry for all my stuttering right now. One of the requirements is that this matrix has to be unitary. And what exactly is unitarity? It's this property here. If I take the complex conjugate of the matrix here, and then it should be equivalent to this as well, and this should equal the identity here. That's essentially what it means for the matrix to be unitary in this sense. I think it's the oh shoot. I think it's the complex transpose, if I'm not mistaken, or this could just be no. I think this is just the conjugate in this instance, but maybe I'll get back to you on that. I don't know why I'm blanking out on this so badly, but there is a requirement that your matrix should be unitary. And even if it's unitary, though, so unitary means that, okay, we can put this on a quantum computer. You can chuck this thing onto a quantum computer and you'll get something. But the problem here, though, is that just because it's unitary doesn't mean it's efficient. And what I mean by that is in many instances, you may come across a unitary matrix, and you will find that relative to the number of qubits on your system, the number of gates required to implement that circuit grows exponentially, which isn't great. That kind of defeats the whole purpose of having quantum computing. But the quantum Fourier transform is really nice because you can have there is an efficient implementation that does not have an exponential level of growth. And when I say growth, you can immediately think, and it's valid to think of it this way, is that we have some kind of big O notation going on. So as some n number of qubits, your growth would go exponentially. Now, with that being said, I want to kind of revisit the derivation here. There were a number of, I think there was one question from last time that I did want to take a look at. And unfortunately, I don't think this member is here with us right now. Yeah, it looks like they aren't here today. But I'll go ahead and answer it because it was asked in the last recording, and I didn't give the most satisfactory answer. I remember mentioning the Vander mode matrix, which is a result of the discrete Fourier transform. So that was, you had omega 0, or omega naught, I should say, omega to the 0th power, remembering that omega is one of the roots of unity. And then you could have, this would still be omega 0 up here, but then you could have omega 1, omega to the 2nd power, and it follows some geometric sequence. And I should mention that a Vander mode matrix is not specific to the discrete Fourier transform. It's actually just any matrix, any square matrix that has a geometric progression in its structure. So that's a Vander mode matrix, but it's just a natural consequence of the discrete Fourier transform. And one of the reasons we see, they were asking, why is it that we see these exponents? Like, why is this 1, 2, and then later on, I'll go down here and it'll probably be 2, and then it'll be 4, and then 3, 6, 9. Why do these exponents live here? And it has to do with the fact, or why the matrix is structured this way. So if we revisit our original formula here, so remember y sub k is our vector, and then 1 over the square root of n, or n is sort of the number of elements in your vector. This is our normalizing factor, I should say, and then we just do this nice little summation here, where we start from, let's see, index of j is equal to 0. And then you would just have x sub j e to the 2 pi ijk jk over n. There we go. So this is our sort of standard discrete Fourier transform. And if I were to just do an example here, don't worry, I'll make it pretty quick here, but just to give you an idea, let's do 4 qubits, or not 4, wow, 4 qubits is too much. 2 qubits. So for 2 qubits, that means that n would equal 4. Just because this is sort of like the number of elements in our vector, and you have to remember that given 2 qubits, you will have a vector, or a ket, that has 4 components to it. So we would have n equals 4, and you have to remember that, okay, for each kind of element, there's like an associated y here. So we'd have y sub 0, and then y sub 1, all the way down to y sub 3. But we'll just look at these two for now, and you'll see where that this matrix kind of comes from. So in this instance here, we'd have x0, and then we just keep plugging in stuff, e to the 2 pi I, and then this is 0 for I and 0 for j. So I and j are just indexing your element, or no, sorry, j and k. Wow, k is indexing this, just like denoting which y you're looking at, and then j is just kind of indexing your x vector here. X is what you're plugging in, by the way. So then you just do this here. And then if you just keep on doing that, you'll find that all the answers for y sub 0 actually all turn into, they're kind of left alone by themselves. Like this exponent will automatically become, this is just 0. So then you just have x0 plus x1 plus x2 all by itself. So nothing particularly interesting here. And then if we go to y sub 1, and then you get x1, still the same thing, x0, x1, and we're still filling out our indices here. So this is just if I were to do everything sequentially. But if I cram it all into a matrix, and we have to remember our definition for omega. Let's see if I was smart enough to. Okay, here we go. Why did I draw it in there? That's pretty terrible of me. Let's see. Omega is equal to Let's see, in this case, e to the 2 pi I, and then j, oh, okay, over n, and then you would have your j and k here. So this is kind of constant, but the j and k which we already see here, will dictate the exponent on the omega, and as a result, we can actually take advantage of matrix multiplication and save ourselves a great deal of time here. Instead of writing everything out sequentially, we can just put it into this nice matrix here. So if we looked over here, remember how, so this e to the, this e to the 2 pi I over n, in this case this is 4, that'll be omega, but this is omega to the 0 times 0 power. And then, so as a result, omega 0 goes here. And then you still see the same pattern as you keep going down this sum. So omega 0, omega 0. And the same thing goes if you went from y sub 1 all the way to y sub 3. You'll still see omega 0s kind of border your Vander mode matrix here. But then you'll notice that in this row in particular, you'll start to see omega 1 and then omega 2. And this should be 4 elements, excuse me. And then omega sub 3. And if I were to go to y sub 2, then you would see omega with the second, fourth, and you'd see that geometric progression as you keep going on. So that's where this is sort of an answer that I'm a lot happier with. From our last session, someone asked an excellent question of why this matrix is the way it is. Why do these omegas have all these exponents? And it's just a natural byproduct of if you were to do it sequentially. You see we have the j and k here in the exponent, and yeah, you're just moving it into a nice big old matrix. And then you would have your coefficients or your ket here, and then you would do the multiplication, and then you just get another nice ket here. Now I do want to make one correction, and this is important because in the last workshop I made a big, it's not a huge mistake, but it still is something that you want to be consistent with. I defined omega, I switched back and forth between e to the power of 2 pi I and then e to the negative 2 pi I. This is just a matter of convention. Different sources will choose to start off with one or the other depending on how they define other elements. But I personally like to stick with just, e to the 2 pi I, just keep things positive here. But as you go into the inverse discrete Fourier transform, the IDFT, which you will see in the next workshop where I will introduce an algorithm that actually uses the quantum Fourier transform in action, then you'll realize that the sign here does become important. But for now, we can just treat it as positive because we're just going to go through in one fell swoop. Now, before I go ahead and show off the actual circuit or how we're going to go from the discrete Fourier transform to our wonderful little circuit, I do want to note that this is sort of an amalgamation of a lot of sources. The IBM Qiskit textbook, I think the University of Michigan had some sources, UC Berkeley, I think the University of North Carolina, I even took some sources from them. The reason being is that out of all the derivations I could see online, I was not particularly satisfied with any of them, simply because of the lack of explanatory detail. There are a lot of assumptions that are being made. And for the most part, if you are a newcomer to quantum computing, even if you're experienced, papers and descriptions tend to be incredibly dense because they assume you're maybe a graduate student or a professional who deals with this math on the daily. But for someone like me, who is just a third-year computer science and engineering student, I think the last math class I took was a linear algebra. So there's definitely a lot of catching up for me. But I hope this added detail will be useful to all of you. And before I go any further, are there any questions so far? Is there anything I might have given a hiccup on, or maybe I didn't explain too satisfactorily, wow, that you would like me to clarify? Once again, I'm always monitoring chat. I've got it in this second monitor here. So if there are any questions, feel free to interject. But yeah, I mean, I just wanted to take the time to sort of review that. Yes, this is our standard form for the discrete Fourier transform. And why is it that we use a Vander mode matrix, or why do the omegas have those specific exponents? It's just a byproduct of if you were to do it sequentially and you just note, okay, well, omega has these exponents or powers, and if we just cram them into a matrix and we perform our matrix multiplication, everything comes out nicely regardless. It's just a nicer way of expressing things. All right, cool. I'm going to assume everyone's, I haven't lost anyone yet. And it looks like I still say the same number of participants. That's good. Was that 4 or 1 qubit? Oh, I don't know whose iPhone. This was, sorry, this was actually 2 qubits. It's neither 4 qubits nor 1 qubit. In the very beginning, with this Hadamard, I said 1 qubit. And then for a matrix with 4 elements, it's 2 qubits, just because of, for 1 qubit, you'll need a vector or a ket with 2 elements inside of it. Oh, hello, Marcos. Wow, thank you so much for showing up. Yeah, so for 1 qubit, we've got 2 elements, and then for 2 qubits, we would actually have 4 elements inside of our so it was 2 qubits for this particular example. I said 4 qubits. I kind of blurted that out of impulse. I was like, oh, 4 qubits will make a. But then you got to remember that that would mean. Oh, no worries, Marcos. It's all good. Most of these workshops are pretty small in number, so I'm incredibly flexible, and as always, we're glad to have you. So because I refrain from doing 4 qubits because that's like 2 to the 4 elements, which for me to draw with my mouse is not particularly convenient. All right. So with that being said, I think I'll go ahead and jump into the derivation. So my goal for today, now that I've kind of cleared up all that preliminary stuff, is I want to show you guys how you go from the math, this summation, to the actual circuit. This is kind of the biggest leap in quantum intuition. And it's not as straightforward as you would think it to be. It's almost like if you were learning discrete math for the first time. It's a lot of proofs and a lot of uncanny tools. But I assure you, the more you practice and the more you get your hands dirty, the more this will become home territory. So I'm going to start with a very blatant ripoff of IBM Qiskit's textbook. Their introductory math is actually pretty nice. So we are applying the quantum Fourier transform to this particular ket here. So ket x. And ket x, there are no specific number of qubits we're dealing with here. It's intentionally left ambiguous because this is very scalable to us. Is actually the equivalent of, and we make this thing here. So this is still the same thing, except I'm going to introduce some new notation, which makes things look a little nicer for the sake of writing things out. So, oh, whoops, excuse me. So then I will go ahead and leave things. So we start with omega. Omega still has their exponents. IBM, most of the time, or in other literature, you will find that people like to switch between x and y or I and j for their indices, just a matter of style. I personally like x and y just because it's like, oh, 2 dimensions, you have your x coordinate and your y coordinate. But a lot of physicists prefer, and mathematicians might prefer I and j, just simply because of matrices. And then we have our y ket here. Now, before I go any further, I want to point out something very important here. This summation, the variable that the summation is working with is y. Now, you also see the y inside of this ket. So what this means is that the ket isn't like a fixed thing in this. The ket is also kind of incrementing. And why it's doing that is because remember how for a singular qubit, you will need 2 basis vectors. So we have this ket 0, and we add it to this ket 1. So these are 2 basis vectors. But for any number of qubits, you will still need some number of these basis vectors. So in the case of 2 qubits, you would need 4 basis vectors. In the case of any other power, you would just keep doubling the number of basis vectors you need. So that's why this y is incrementing. Because if you remember, if I go all the way back up here, we have x sub 0, x sub 1, x sub 2. These are just kind of, you can think of them as your bases as well. So that's why this y is targeting this ket. And I want you to really keep that in mind. This is kind of the key here, that this y is targeting that ket, because it will come back to bite you if you don't remember it. So, but this is just nothing weird here. This is our standard definition. I haven't done anything fishy with it. You will notice though, this is IBM being clever, I guess, or maybe someone got lazy with the latex here. X and Y are exponents. The n here, the n is actually meant to also be kind of like dividing the x, y, n as well, but they opted to just write it as subscript. And I will follow that same convention. In case you guys want to go visit the Qiskit documentation and see an alternative explanation, it'll still line up with it. So let's go ahead and do one thing here. Like any just to kind of remind ourselves what omega to the power of xy sub n actually looks like. So let's go ahead and, oh wow, okay, see my sigmas look absolutely terrible, but let's see, n minus 1. And then we're still working with e to the 2 pi I xy over n. And this is all over n, by the way. And then we still have our handy dandy basis ket sitting here. Okay, so all we've done is expand the definition here. But I'm going to introduce some mathematical sleight of hand here. And this is kind of the one of the pivotal things you got to see. Now, this y, or this n, I should say, y and n, excuse me, can actually be split up. The y over n component right here. By the way, I should probably mention what n is. N is, once again, the number of elements in your vector. So it'd just be 2 to the n, where n is sort of the number of qubits you're working with. So if I have, say, 2 qubits, just 2 to the 2, so that'd be 4. So n would just be 4. So this would, by default, be equal to 4. But I'm going to, there is a way to express this in terms of a series of fractions instead of just one value. And in the beginning, this probably won't make much sense. Like, why are we bothering with making this any more complicated than it already is? But it is a necessary evil to get this into a bunch of smaller chunks that can later be implemented as circuits. So I'm going to go ahead and do what I just said, and maybe once you see the math, it'll sort of make a little more sense here. So e to the 2 pi. Oh wow, whoops! I totally omitted the sigma. The sigma does not disappear, by the way. Here we go. Here is our good old capital sigma, of course, with y equals 0. And then we have, let's see, e to the 2 pi I. It stays the same. Nothing particularly fishy here. But now I'm going to introduce this guy. And the IBM documentation does do this word for word. So 2 to the k, and then x is, we don't touch x, we leave x by itself, but we're going to change how we express y here. And we're also going to do another thing here. This is going to be kind of confusing. Notice how I've just blown up the vector here, our basis vector. So instead of just having y by itself, now it's y sub 1 all the way to y sub n. But before we worry about this, let's kind of take a look at what's going on here. So the basic idea is, if you'll note that we have this value of y sub k over 2, and this can be broken up into a number of fractions. It's actually, like, I'm just going to write out an example here. So e to the 2 pi I, so this remains untouched. But then if I look at our exponent here, I can have y sub 1 over 2 plus, and I go on here, and this would just be y sub 2 over 2 to the power of something. This would be 2 to the power of 2 plus y sub 3 over 2 to the power of 4. So this is kind of, and you could keep going on as much as is required by a particular instance. This is kind of fractional binary going on here, because you have some value of y over n, and we opt to break it up into a number of fractions, with the denominator at the power of 2. And of course, doing this action here is kind of hinting at the fact that we're going to transition over from having our normal happy integers into binary. We will start counting using ones and zeros, but that does become advantageous later on when we're constructing the circuit here. So with that being said, I'm going to keep on kind of doing this expansion here. And so yeah, all we did was break up. We just took what was originally y over n. Oh wow, that looks like an x. That's terrible. Hold on. We took y over n from the exponent here, and we've decided to express it as a summation. And in this summation, we've just broken it up into what looked like just a series of fractions here. And these are equivalent. If you don't believe me, feel free to verify yourself. But now I'm going to just be a little more verbose here, and the verbosity will kind of make sense as we keep going on. In the IBM documentation, this is where my explanation and IBM diverges. IBM likes to introduce the capital pi notation Capital Pi is like summation notation, but it just means you multiply a bunch of stuff together. But I opt to omit that for the sake of just seeing things as they really are. So we're going to do 1 over the square root of n. We still keep this guy here. This guy's just sitting here. It's sort of to the side. So I just put this here to remind us that it's not too important to worry about this just yet. But now we have e to the 2 pi I x over y to, let's see, y sub 1 over 2 to the power of 1. Let's see, times, let's see, e to the 2 pi I x y sub 2 over 2 to the power of 2. And we can keep on sort of going with this summation here. But eventually, we will get to a term that looks like this, e to the 2 pi I with x over, let's see, y sub n over, let's see, 2 to the n. And this n, by the way, I should have meant, if we go back up here, I should have, wow, that was not particularly good of me. I should have mentioned that this k here, this is k is equal to 1, and this k goes all the way to n. And this n is this n is the same n that normally for the circuit implementation, it's just the same n here for like the number of qubits essentially. So now I've written this whole thing out. Here we go. Let's go ahead and do this. So it's just, all I've done is I've taken this summation here, and as well as a property of the exponents, right? So if you have added exponents, that means like the actual values themselves are just getting multiplied out. And we have all these individual phase factors just kind of sitting out here. And we still have our vector here, y sub 1, dot, 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 and then y sub n. And that's all cool and good. Now, here's another thing. I'm going to expand our summation. So what do I mean by expanding our summation? So in the very beginning, earlier in the derivation, I noted that we did this thing here. We took this ket, which is normally an integer. So normally I'd just be like, oh, so this would just be, let's see here. I think it's y is equal to, right. Is it y equal to 0 or, oh, I might have gotten my indices mixed up here, or maybe not. Let's see. This is where my handwriting comes to bite me in the butt again. Sub k, and then okay. So no, that's that is a moderately different summation going on here. But anyways, the basic idea here is instead of expressing each basis vector, as like, okay, this would be sort of basis 0. There we go, basis 0. And then, okay, now we have some coefficient for basis 1, and then basis 2, and then basis 3, stuff like this. We're just going to express it all in binary now. So, this might be, in the case of 3 qubits, this would just be 0, 0, 0. Then you'd have 0, 0, 1. And then 0, 1, 0. So that's kind of how we're, that's what I mean when we're kind of breaking up, like why we bother doing y starting from 1 all the way to y sub n. That's all that's going on here right now. And as a result, we can do this with our summation. This is kind of what I've been trying to get at. Wow, that's definitely not ideal. Okay, then we just have, it looks like a bunch of sigmas just kind of chilling out here. But the reality is sub, okay. And then we still have all of these multiplicative factors just kind of sitting here. But now what I'm doing with these sigmas is I'm saying, okay, look, y sub 1 can be equal to 0, or it can be equal to 1. And then y sub 2 can be equal to 0, or it can be equal to 1. And then y sub 3, or actually y sub n minus 1, so the term before the last term is equal to 0, and then can also be equal to 1. So that's just me going through. So remember, like we have y sub 1 all the way to y sub n here. I'm just sort of incrementing through our basis vectors in binary. So that's why I can expand these summations to look like this. And then you would still have your exponents here, and then you'd still have y sub 1 dot 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 all the way to y sub n in our sort of placeholder vector here. That's more of what it's like. Now, I kept doing this kind of, actually I should show that for this particular summation, the actual exponent that goes with it is, let's see, 2 pi I, let's see, x, y to the n minus 1 all over, let's see, 2 to the n minus 1. So that is the multiplicative factor that kind of goes along with this particular summation. You can see it's targeting n minus 1 equals 0 here. And there are multiple subscript y's in here. So it's y sub 1, y sub 2, dot, 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 all the way to y sub n. And each y is supposed to represent like one qubit. And it looks kind of confusing when they all group it together. What's actually going on here is, okay, 1 qubit, and then we do this guy. This is called the Kronecker product, which combines the different qubit states to make one coherent quantum state. And then we do y sub 2, and you take the Kronecker product again, and then you still have y sub 3. Here you go. And you can keep on going for as many number of qubits that you have. That n, once again, is the number of qubits. So there you go. That's what it looks like. Oh, and I just realized, okay, this y here is distinct because this is kind of referencing the number of, like if I went to the very beginning here, you would have y sub 0, y sub 1, y sub 2, and these would all be in like, kind of one vector here once you got your result. Whereas these are kind of targeting qubits, and then the other sequence here, or I start indexing at 1, is because of the number of qubits. And this is more of a lack of oversight on my part. I would have chosen a separate character instead of y in 2 places, but I was trying to, once again, I'm consulting 10 different sources here. So I'm trying to glue together 10 different explanations and see if I can get the most clear one out of it. Now, I want to, in this whole summation here, I'm going to take out the nth term in this summation. What that's going to look like, the nth term is the last term, by the way. What that last expanded summation, so y sub n, is equal to 0 here, and then over, 0 or 1, then e to the 2 pi I, and then x, and this time it's y sub n over 2 sub n, is, and then we would have our ket here, our ket y sub n. This is a single qubit, by the way. You notice there's only one value here, so that tells you there's only one qubit. And then here we have the coefficient or the factor in front of it. And then this is telling us that, okay, so that means y sub n can either be equal to 0 or 0 plus 1, ket 0 plus ket 1. That's what I meant by expanding. So they have all these summations kind of chained together. Is because you're literally flipping ones and zeros in binary, which denote which basis vector you are targeting in the particular sequence. That's what I mean here. And what this is going to look like, well, excuse me, what this will look like when you fully expand it is for ket 0, nothing happens. But then for ket 1 here, then we see, oh, wow. Actually, I don't know why I wrote it this way in my notes, probably because I was in a rush here. But then we have this coefficient kind of sitting e to the 2 pi I x over 2. And then this is just because, yeah. At this point, y sub n is equal to 1. So you would have a 1 here, and then this would just be 2 to the, this would just be like a singular instance as well. Then 2 over the ket for 1. Hold on, let me clean this up a bit. Over 2. Okay, cool. And that's, of course, assuming that n is just, this is just for a singular qubit or term, I believe. I apologize for being a little sloppy with my terminology there. But this is essentially what happens when you're targeting kind of your nth term here, or the last term, I should say. Right. Over 2 to the, no, the n should be here. Sorry, I totally left that out. But you'll notice that this now represents, or at least we have two coefficients here. This is 1, and then this is the actual phase changing factor, and this describes one qubit. So now that we've really gone through all this grease to break the whole quantum Fourier transform down into this very convoluted format, what actually happens is I can now express this guy. So we started out with this expression here. We can now express it in terms of this one singular instance here. This 2 to the n is actually equal to 2 to the n here. These are equivalent expressions for this particular problem. So I have ket 0 plus, let's see, e to the 2 pi I x y over 2, and this would be 2 to the 1, and then you'd have ket 0 here. And then I could have the same thing, except now that exponent would be to the power of 2 to the power of 2, 2 to the power of 3, and you just see it's just a bunch of these kind of terms in parentheses here, and they're all there's an implicit Kronecker product that's kind of hanging out around here, which just means that all these individual qubit states can be kind of combined together. So we'd have ket 0 here, let's see, plus e.
Hey, John?
Yes.
Quick question. You said 0 plus, and then there's that phase, and then you did 0 ket. Should that be 0 ket or 1 ket?
Oh wow, holy! That's a that is a 1 ket. That's
okay,
ket 1.
Thank you.
Yes. No. That, excellent. Thank you so much for pointing that out. If there's a qubit with 2 kets, basic linear algebra will tell you that they are not orthogonal, and you probably wouldn't be able to accomplish anything useful with 2 kets and a phase difference. So then this would just be, this is kind of the last multiplicative term here. So then be ket 0 plus e to the 2 pi I x, and then y over 2 to the n. And then there are other terms that are lingering out around here, depending on how much you defined n as. Now, with all this being said, this still doesn't look like it's any closer to being implementable in a circuit. It still looks like a very convoluted thing. I don't doubt, if I lost you and all the other derivations, please do forgive me. I noticed there's like an indexing issue. That's a fault on my part, but your patience is much appreciated. So now we still have to do one more interesting transformation here, and it has to do with y here. So I'm going to introduce yet another manipulation here, and it's still this lingering y over 2 to the n, I should say. So if you'll notice, we still have for each qubit, for what it looks like for each qubit, there's this phase that keeps sticking around here. So e to the 2 pi I, and over, let's see, y, and then 2 to the k. And then we remember that k is kind of just like the cap here. The k that I'm talking about is the exact same k that was up here. So, k equals 1, and then all the way to n. That's what I mean by that. So k is just another variable that's kind of hanging out there. And, just to be thorough, the bounds are this. K less than n, once again, n being the number of qubits we're interested in. So what I'm going to do is I want to kind of take advantage and redefine this y over 2k. And we're going to introduce the fractional binary system. So what is fractional binary? Normal binary or any number system works with having, like, when we say base 10, well, that's just because you have 10 to some exponent, 10 to your ones place, and then your tens place, your hundreds place. So if you tell me 101 things. So it's one of these, 0 of these, and 1 of these. And for binary, it's the same thing, except we do 2 to the 0, 2 to the 1, 2 to the 2, and you get the idea. This is for nice whole numbers. But it turns out that there's actually a way to express the decimal component. So in decimal here, and I could tell you I have 101.1 Dalmatians. Why you have a tenth of a Dalmatian, I really don't want to know. But this placeholder here is the equivalent of 10 to the negative 1, 10 to the negative 2, 10 to the negative 3, and we're just decrementing our exponent here, which represents 1 over 100, and this would represent 1 over 1000. So this is what I mean. So if this is just the normal decimal system, then the fractional binary system would just be 2 to the -1, 2 to the -2, 2 to the -3. And you'll kind of notice this makes a nice pattern here. 1/2, 1/4, 1/8. And if I just keep going on and on here, and you'll notice that this is this is y over 2k. And lo and behold, we can actually express y over 2k as a summation of these positions here. So actually, there's a specific notation that we like to use. You have your whole number component in front, and then we would just have y sub 1, y sub 2, y sub 3. These would just be your, or we essentially take y, and then it gets broken up into these other components here. Oh, and by the way, these y sub 1s and y sub 2s, these are the exact same indices that we were using earlier for a ket. So remember, I did this transformation from, okay, y is a whole integer, but now we're going to express in terms of binary. So y sub 1 dot 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 all the way to y sub n. These are the exact same kind of values that are going on here. So this expression that I just wrote out here, 0 dot y sub 1, y sub 2, y sub 3, this is just the equivalent of y sub 1 over 2 to the 1 plus y sub 2 over 2 to the 2 plus, and then I could keep going here. But this is what I mean by fractional binary as a way to express kind of the y's that get thrown in here. So with all that being said and done, let's go ahead and once again rewrite the whole thing again. But still 1 over the square root of 2 to the n. And let's see here. We still have our ket 0, and keeping in mind that we're still dealing with ket 1 and we're not going to rewrite another ket 0, excuse me, 2 to the pi x. So instead of having that y over 2 to the power of 1 that we saw last time, now we write it as 0 dot y sub 1. And this would just be ket 1. And then for our next term, I really wish I could circle this, copy and paste it, but this is, I'll have to find a better application to do that. But for all the other terms here, then it just becomes 0 dot y sub 1, y sub 2, and then it just be 0 dot y sub 1, y sub 2, y sub 3. And the way to think about this is we still have, normally it would just be like, y over 2 to the n, right, for each parenthetical or each parentheses that's containing one of these terms in it. But now the 1 over 2 sub n is accounted for by each of these y sub 1s in the fractional binary notation. So that's all we're doing here. And the reason why for each term we go from, okay, y sub 1 for the first, and then y sub 1, y sub 2 for the second, and then the third and its exponent would have y sub 1, y sub 2, y sub 3, is because now we're going from 2 to the 1, which is just equal to 2, and then from here you would get 2 to the 2, but you would still have you still want to include the other beginning factor here, because we're kind of counting or we're representing y divided by some exponent here, and we're breaking it up in a series of fractions here. So, and we're using binary because normally y would just be an integer. So now we have to use binary. So we've accounted for both the denominator as well as the numerator, which is why you just have these growing numbers of y sub n's. Y followed by a sub of some number that's getting indexed. Now with all that said and done, now we can actually kind of try and see what the circuit form looks like. And this is really the secret sauce here. So I was kind of expressing our vectors like this. Okay, y sub 1 all the way to y sub n. So now I'm going to break. I'm just going to look at one qubit. Let's look at our friend y sub 1 here. Why not? Y sub 1, and then the rest of the circuit is just y sub 2 dot dot all the way to y sub n. And once again, implicit Kronecker product. Just to save time, we won't bother drawing in that circle and the x inside of it. If I apply a Hadamard gate, the first thing that happens, it kind of gets us one step closer to what we want. Ket 0 plus e to the 2 pi I, and this time you would have your 0 dot y sub n, just kind of sitting out here. Whoops, excuse me. this is still the fractional notation here. Or no, not y sub n. Wow, that's terrible. Should be 1. There we go. And then this would be ket 1. And that brings, so that's just applying one Hadamard. But you got to remember that, we have for each qubit, I mean, we're adding kind of, there's another y sub 2 and there's another y sub 3 and a y sub 4 that will incrementally have to be added. So if, we apply the Hadamard to 1, now we take advantage of the fact that if we want to add y sub 2, we're going to use a controlled rotation gate. The y sub 2 indexing kind of the second qubit, and so that controlled rotation is controlled by the second qubit, and that will help add the extra phase factor we need, because you got to keep in mind that we're still dealing with rotations of pi over 2, pi over 4, pi over 8. The pi is just dangling on the exponent, I should mention. Normally, I know this isn't like the clearest bridge between e to the pi I and then just having this, but most of the gates are labeled that way, not because the matrix, the way the matrix is expressed, has that notation in it. But I think it's a lot better if I draw out what the actual thing looks like. So I mentioned we applied a Hadamard first, and now we have a controlled rotation. So the first rotation is let's see, controlled pi over 2, and this is controlled by the second qubit. And then we have a controlled pi over 4, and this would be controlled by your third qubit. And all these control gates do, by the way, is like if this is 1, if this qubit was in ket 1, it will apply the rotation. If it's not in ket 1, the rotation will not be applied. The phase factor simply will not be added. And then this would be pi over 8. And then if you go all the way down, it would just, and you can keep doing this for each of the, depending on how many qubits you have. And just to finalize things, this is QFT on 1 out of the 4 qubits here. To do the other one, you still do the Hadamard, but you won't have the pi over 8 anymore. It would just be pi over 2 and pi over 4 on the second qubit here. You don't need the other, just because, like if you look at the terms here, like if I were to do what I did above, but I only used y sub 2 instead of y sub 1, I would not need the same number of decimal places, which would equivalently be the same number of sort of phase factors that get tacked on to each of these terms in the parentheses. Now, one of the things I want to point out before I kind of wrap things up here is sometimes, okay, depending on how you're doing this, you have to be careful about the ordering of your qubits. IBM does this thing where they, I forget which one they choose as the most significant bit, because I don't live in Qiskit the whole time. But sometimes what happens is you'll have to, at the very end of your Fourier transform, you have to perform a bunch of swap operations to kind of get everything back in the original state that you originally had it planned. Or you can kind of rearrange the circuit to try and avoid it. But the way the math comes out, this is like the most straightforward expression of that. So after all this math, you sort of see why it's not as intuitive to go from the math to the circuit form. And trust me, I was pretty disappointed to find that out myself, because you see this unitary matrix and you think, okay, you've hit like a home run, like you're done. We have the unitary matrix. Now all we have to do is figure out how to decompose that matrix. And modern day quantum compilers don't actually do all this analytical nonsense. There are a number of standardized ways to decompose such matrices down into your desired gates and elements and whatnot. But this is the sort of raw math behind everything that's going on here. And once again, I do realize my choice of indices weren't great, but hopefully later on I will have a textbook entry, with all the math written in LaTeX, as well as a Jupyter notebook, so you can kind of see, or you can play around for yourself what I might have failed to explain as well as I hoped. So that being said, just once again, just brief overview. So we started with the basic formulation here. It's this really nice summation. And we sort of went from, recognize, we just expanded things out, we just blew it up. So omega is still this guy here, but then we take advantage of this definition of y over n. And we leave x to its own mechanisms here. And the main idea that I want you to keep in mind for going from the discrete Fourier transform because this is still the discrete Fourier transform in definition. In fact, the QFT and the DFT are actually pretty much identical. But to go from the DFT into the actual quantum implementation is all this math that I've just kind of done here that will take you. Let's see if I can zoom out here. No, okay, hold on, let me. Okay, cool. I can zoom out and kind of see the whole thing going on here. But to go to the quantum state, you have to introduce this interesting little fractional binary indexing system, which allows you to break up your y's. And then we can exploit the properties of exponents to do this nice summation decomposition, keeping in mind that we're indexing or our basis vectors from integers. Now we do it all in binary. And that lets us, now we just Kronecker product all these things together, and with a combination of a Hadamard per each qubit, followed by a number of controlled phase rotations, or controlled rotations, excuse me. That's phase rotation is a bit of a redundant term there. Then we get the sort of quantum Fourier transform. There is an inverse quantum Fourier transform. I won't show that now. It does come up in a lot of other circuits, but the one of the neat things with quantum computing is that all results are reversible. So if you push something through a circuit, if I push it backwards, it should give me the original state. It's not like traditional computing where if you have a singular logic gate, like an AND gate, you have 2 bits of data and then you get only 1 piece of data, and that other piece of data gets permanently lost in the form of heat or entropy, which is so that's why I can't take this 1 and kind of go backwards. But with quantum computing, you can do that. So that sort of wraps up what I had in store for you all. Are there any questions? I know there are probably like a lot of lingering questions, or there's probably some parts of my explanation that could have definitely been improved. But I hopefully I will have a more concrete document for you guys to look at that will clear everything. That'll clear everything up. But yeah, this is like the explanation that I'm personally the happiest with, because a lot of other sources, like the Qiskit textbook, will condense this down into 5 lines and say, okay, now you should be able to figure out what's going on. So I'll leave it at that, and I'll open the floor to any questions. Oh, and once again, Amir, thanks for pointing out that hiccup with the ket 0 and the 2 ket zeros.
Oh, that's no problem. I know you did that on purpose to check whether we're following along.
Right. Amir's
as any good teacher would, right?
Absolutely, Amir's right. I have intentionally bugged the problem.
No, this is a great this is great. I mean, I like all the detail you went into, with all the expansion, because, that, yeah, I find in the material it's not usually dealt with that way. It's like, oh, well, we'll leave that to the reader to expand out and make sense of, and so it's nice to see that here. I was going to add one comment. I know we're almost at time, but it's only because I didn't go through all the formalism that you just went through, but kind of discovering some neat qualities of QFTs. I used a QFT for counting purposes in this challenge, that monthly challenge from QOSF. There was the second challenge was to figure out the Hamming distance between 2 bit strings. And what's fun is you can actually use a QFT. You can use a QFT kind of like, so I was treating a QFT register to count. And what's neat is you essentially have 2 clocks going, you have 2 counting mechanisms across all these bits that you're talking. So your Y bits you're talking about, I was looking at more from registers that count in a specific modulo, which is very similar to, it probably makes sense. I could maybe just copy this in the chat. It might make sense better that way. But it's cool to see you describe this more formally, because now I'm realizing, oh, I was just kind of discovering some of these qualities experimentally. So Yeah, so what this is just, I put these in my comments so I would know what I was doing with this QFT Hamming distance counter. And essentially what I saw was in a 3-qubit register, that like, depending on whether you're most significant or least significant, that far bit actually you could see as like it counting clockwise or counterclockwise. Like even if you're looking at it on a block sphere. So like for instance, at register 1, for anyone who wants to follow along, I pasted in the chat, like for that first bit. So, you know, I guess this would be like Y3 in your example, that's counting, you know, modulo 8. And then like this other term, or, you know, maybe I could refer to it as terms, because, you know, when you expand it out the way you did, you have phases you can throw in front of each term. And so, it was cool because like, yeah, like it's kind of like you can control counting just by linking phase gates to those individual address lines on the for the register that you would be using a QFT with. Um, I know that was kind of a rambling explanation, but it's just fun. Yeah, it's kind of neat to see like the different ways you can use QFTs.
Oh, not at all. That's actually, you mentioned this modulo, and actually I'm really glad you did mention that, because that is one of the sort of main reasons that QFT gets thrown around so many times is you know, period counting, which, you know, that term doesn't make much sense now, but if I were to go into Shor's algorithm, you know, that's definitely something that's used to figure out, to help with the factorization process. And this is an excellent observation. It's a very nice, I would argue, a much more intuitive way of looking at things, because it took me a while to get this mathematical formalism down. And you see that even when I try and present it, there are a number of parts where my brain just kind of hiccup here and there. So I do appreciate the patience. And I hope to, you know, once again, get this stuff down more in more concrete documentation for you guys to refer to in all of its glory, because I sympathize with you, Amir. I mean, I'm not a huge fan of of the whole, okay, here's 5 lines of very dense math, and then we won't explain where we're coming from. So this is once again, this is pieced together from, I think I was looking through my tabs when I finished developing this explanation. I think 10 different sources: Qiskit, University of North Carolina, University of Michigan, UC Berkeley. Because each explanation is always missing something that I think should be there to kind of explain why it is the way it is. So I've tried to take the best of each one, and you can see, you know, my indices weren't the best choice, but that's because I'm eyeballing. I'm like, okay, this explanation was good for this, but that explanation was pretty terrible at this, and eventually, you know, they kind of coalesce and make one very nice product. All right.
Yeah, thank you. Yeah.
Yeah, you know, once again, I'm incredibly happy to have everyone in attendance today. I realize I'm 3 minutes over, so if there aren't any further questions, you're, you know, more than welcome to go. But once again, thank you so much for coming. Next week, I haven't settled on what I want to do just yet. Ideally, I'd want to do something with the QFT, but I might decide to go into hardware. I remember I promised hardware last time, and I put a pause on it because I didn't finish my QFT explanation. And mostly in part because there was that one member, I can't remember his name, but he asked a question I just answered in the very beginning, which is like, why are the omegas, why do they have exponents in that pattern? And it's just a matter of, if you expand the whole thing, you will see where that pattern comes from. Once again, thank you all for your time. I hope you all have a wonderful weekend. Thank you.
Thank you all for coming. Yeah, John, that was pretty great.
Yeah, that was awesome, man. And Amir, like that was a very cool use case. I didn't really think about for sure. I mean, I think my mindset has definitely been like, I think John and Kirk and Marcos would tell you that like mine has always been around the biology and like how Fourier transforms are pretty much so commonly used in biological calculations. Like all of the major like protein softwares, protein docking softwares and whatnot use Fourier transforms. And I can definitely see QFT as being like a direct analog for making that conversion form protein structures into signals that can then be used for better analysis. And so it's interesting to see that like we have this framework with which we could really make processes on quantum computers for protein analysis very accessible for the information that we already currently have, as it's not like wholly different from what we're already doing. So yeah, I'm very excited about that. This algorithm for that reason. I think it's there. And yeah, I always just wonder kind of what the bounds are for this work, because I feel like it could definitely be used in music, for example, noise analysis, that kind of stuff. I feel like it could definitely be used in a lot of different use cases. Well, actually, that's a question I had for both of you, John and Amir, is have you considered this in terms of use for speech recognition, like natural language processing, that kind of stuff? Or is that still like too far in the past the NISQ era kind of stuff?
Oh, I mean, I don't know like how you would cram that on a quantum system. I mean, the closest thing I can think of is just like, okay, the classical system. Like maybe Amir might have a thing or two to say, but.
Oh yeah, I don't have a lot of experience with like signal analysis or or even audio processing in general. So yeah, I can't really speak to that. Seems like a cool application. I kind of wonder for the, because we have a data loading problem, if we ever have, I mean, that would be quite a stretch, but quantum sensors that spit out quantum data, well, okay, maybe, yeah, maybe there's something there, but yeah, I don't know. I think it would be hard to load the data sets.
Yeah, I think it's funny you mentioned that. There's Jonathan Hui. He is I think he's a researcher, because if you literally look up any algorithm, he's written some medium related article and just point out, I don't know if it's the same thing or it is a similar problem to what you're saying, Amir, about loading. I think he was, in terms of QFT, he was talking about loading coefficients or getting like an initial basis configuration is kind of difficult. So I see what you're getting at, but I just remember when I was researching this QFT, his explanation was like pretty decent, and then he lost me. He really, like, the moment he introduced those binary, the fractional binary is what really got on my nerves, because I couldn't find like a satisfactory way of explaining it. And then I don't fault any of these people for writing it the way they do, because they're targeting different audience levels. I mean, I developed these workshops in the mind sense that there are probably people like me who stopped their math somewhere at linear algebra and never bothered going any further. So
well, I'll say when I was I don't know if we're trying to end the meeting. Yeah, sorry.
No, it's all good. I mean, I hope we're not holding you against your your time.
No, I mean, it's COVID times. What am I going to do on a Friday night? But no, it's funny because so I went to undergrad in 2003 at Georgia Tech. And I got to tell you, I think linear algebra, the way it's taught, has changed since then, because I am now seeing linear algebra again and wondering, whoa, either I was like asleep at the wheel, or they just didn't cover a lot of this stuff when I took it back then. So yeah, that's where, like, that's kind of an aside from what you're talking about. Like you were talking, well, yeah, you were saying the last time you dealt with math was linear algebra, but like, I'll tell you, I think the linear algebra courses today are much better than they were like 17 years ago. So
I'm glad to hear there's been an improvement. Yeah, that being said, I think I'll go ahead and stop the recording here.